Alright, this is week five's group problems. I decided for this week that since each of the questions ask you to do a very similar process, what I'll do is walk through the first question in detail, and hopefully that will help you with the remaining questions. The first question was focusing on corn, 3 different traits in corn, and all of the questions in the group work more or less focused on these 4 things. So first they usually ask for you to determine the allele arrangement for the heterozygous parent, to be able to determine what the gene order is of the 3 linked genes on the chromosome, be able to construct or figure out the length of a linkage map with the 3 genes, and then calculate the interference. So for the corn, we have these 3 traits. We have the color, so if it's dominant, then it's colored. If it's recessive, then it's colorless. We have a waxy trait, so if there's no wax, that's the dominant trait, and if they're waxy, it's recessive. And then the size, so if they're plump, that's the dominant trait, and if they're shrunken, that's recessive. So you'll see these visuals a lot. These have been a little confusing to some people, so I'm going to walk through it really quickly. This is showing, for the cornet, it doesn't matter gender so much, but usually you'll have the female and then the male who are the parental crosses, and they'll look like this. This is not a division problem. This is showing, basically the line that's here is showing a separation of homologous chromosomes. So if this was a female here, this would be one of the homologous chromosomes and that would be the other. And then so together this is showing the 2 homologous chromosomes for the female. And then the same thing over on the other side is for the male. For any of these tri-hybrid crosses, you are going to have one parent that is heterozygous for each of the traits. So right here it's heterozygous for the color, heterozygous for wax, and heterozygous for shape. And you're going to have one parent that is homozygous recessive, always. And for all intents and purposes, we completely ignore this parent when we're figuring out all these problems because they're just kind of there as a base to understand the heterozygous parent. Okay, so when we do this cross, the trihybrid cross with these 2 individuals, even though they're corn, we get this variety of phenotypes in their offspring, in the F1 offspring. So this is showing the different phenotypes for the offspring and then the number of offspring that had that phenotype. So our first step is to determine the allele arrangement. So what you want to do when you're looking for the allele arrangement is look for the 2 F1 generation groups that have the most. So you're looking for the phenotype that has the most offspring, the top 2. So right here, I marked them off. The colorless waxy plump corn and the colored non-waxy shrunken corn would be what are considered the parental offspring, or the 2 sets of offspring that have that are the largest for a certain phenotype. When you are determining the offspring's genotype, I laid it out here. You're always going to have the homozygous recessive parent. I just put them on the bottom there. So this part, this chromosome, we got from them. And then we're going to determine the other, excuse me, the other chromosome from these offspring. So we have the colorless, waxy, plump one. So right here we have the colorless, waxy, and then this one would be plump because of the dominant. And then we have a colored, non-waxy, shrunken, which is right here, colored, non-waxy, shrunken. And that way we are able to determine what those offspring would look like. We take that information and then we're able to figure out the allele arrangement from it. So what we do is we take these 2 top ones, because we're assuming that we got them from this heterozygous parent, and we combine them together. So I took this one right here and put it down there, and took this one here and combined it right there. And then we use that combination to determine what the original parent was. So we are not necessarily determining where the C or the WX or the SH goes. We're simply deciding on which of the chromosomes is the recessive trait, on which chromosome is the dominant trait. So we can see here that on the top chromosome, we're going to have the dominant C, the dominant WX, and the recessive SH. And on the other chromosome, we're going to have the recessive C, the recessive WX, and the dominant SH. And so up here now, I just switched that so it's more accurate. Okay, so the next step after we figure out the allele arrangement is to determine what the gene order is. So what order are the C, W, and WX and SH in. So what we do is we take what we know from this heterozygous parent and we set up the 3 different ways those genes could be ordered. So the first one I set up just like we have it on the top. And a good way to keep track of this is to alternate which of the traits is in the middle. That's kind of the easiest way to keep track. So another alternative would be to have the shape gene, so the SH, in the middle, and then the third alternative would be to have the color gene right there in the middle. Next, we want to figure out what takes place when a double recombination occurs on these. So double recombination means that a gene switches and then we have a second time when there's a switch. And the best way to keep track of that is instead of having one of these outside alleles being switched, you will see that the central allele is the only one that really switches in the end. That's the best way to keep track. So once we've set up our 3 different arrangements for the alleles, or the genes, and we have them go through a double recombination, we rewrite what they would look like. So here, it's the same layout except that the central genes, so here's the W, here's the S, here's the C, get swapped. Okay, that means that they've gone through a double recombination. Our next step now is to find the 2 phenotypes of the F1 offspring that would be double recombinants. So the ones that would, and those are the ones that are the least frequent of the offspring. So the best way is just to go through and find what are the 2 groups that there are the fewest of. And in this situation, the group here with 20 is colorless, waxy, and shrunken, and the group with 15 is colored, non-waxy, and plump. You determine what those alleles would be, and by determining that, you can know which of these 3 options is the actual possibility. So when we look through the different options, these are the only ones that match the phenotype. So this one here would be the colored, non-waxy, and plump, and this one down here would be the colorless, waxy, and shrunken, and these other options are not available to choose from. So just by process elimination, we can know that this is the order that the genes are on the chromosome. So I'm going to take this and switch it over. First, I'm switching it over so that we have consistency with the dominant and the recessive that we determined at the very beginning. So for example, the original parent had the dominant C and W on one chromosome and then the dominant S on the other. So I just wanted to make sure we did the same thing here where the dominant C and dominant W were on one and S was on the other. Then I also wanted to show that you could lay these genes out in 2 different ways and it would mean the same thing. So whether I have the C first or the W first, so long as the S, the shape gene, is in the middle, it doesn't matter which way you write it. So I'm going to take this layout, the gene order, and I'm going to replace it up here with our original parent so we have, again, a more accurate layout, and also switch, even though we don't really pay attention to the other one, switch that one as well. Okay, so once we've figured out the allele arrangement and the gene order for the heterozygous parent, we can start building and identifying the linkage maps between the genes. So the best way that I can do this for the process is I like to lay out what the 4 offspring phenotype would be in a recombination and kind of have that visual. Now, just to back up, bear in mind that we need to do this twice because we have 3 genes. We need to figure out the linkage between the W and the SH, and we need to do the whole process again for the SH and the C gene. So right now we're going to focus on the WX and the S gene. What's the distance between them? So to do this, first we need to have recombinations take place. So the first one we're going to do is a recombination if the S gene swapped. So I'm going to have that take place right here. The dominant will move up to the top and the recessive will move to the bottom, and again it doesn't matter what happens over here because they are the same. And then we're going to take those swap genes and place them with the corresponding other parent down here. So for example, we'll take this top set and combine it with that one there to give us one of the offspring phenotypes, and that one matches up over here with this set. So the colored non-waxy plump, and then we just take the number of offspring that we had, and I put it down there to keep track. And then we want to take the bottom portion after the recombination takes place and match it up here. Find it on this side and tally up the number that there were there and include it here. Next, I'm going to swap them back to their original position, just this top parent, just so we can keep track. So now this is how the parents' gene order and alleles were originally. Now we're going to do a recombination with the W, with the wax gene. So that's going to swap, and now we're going to match up with the last two here. So we're going to take the top set there and combine it down and then find the group. So there's 951 of those. We're going to take the bottom set, match it up, find the group. There are 974 of those. And we are very close to being done. So the final step that we want to do is we want to tally up the total number of offspring that were there. So if you add up all of these numbers here, you're going to get 6,708, if I did the math right. I was kind of typing fast. And then we plug them into the equation that they gave you. So we add each of these sets together and we divide by the whole amount. And then we multiply that by 100. And then we have our map units. So for the WX to the SH genes, there are 29.22 map units. Okay, we're almost there. So now that we've determined the map units between the wax and the shape gene, now we need to repeat the process for the shape gene to the color gene. And since we've kind of done it through once, I'm going to go a little bit faster just to save on time. I make long videos. Okay, so first we lay out the 4 different phenotypes that we can make. We do a recombination. I'm doing that with the shape gene. And so we'll switch there and then we start matching up. So the top will match up there and then we find those offspring. So again, that's the offspring. There's 15 of them. Take the bottom portion, find which offspring those match up with, and there's 20 of them. Okay, and now I'm going to take the heterozygote parent and put it back to its original setting. That's how it normally is. And we're going to do the other recombination with the color gene. So let's take the C, swap it, and then match them together. Oh, I missed my little yellow squares. Okay, so we take the top one, go there, and then match. And over here, this phenotype is colorless, non-waxy shrunken, and there's 84 of them. And the bottom portion matches to the colored waxy plump, and there are 99 of them. Do the same thing. We have the same total number of offspring, and now we're adding up these 4 phenotypic groups. So we have 15, the 20, the 84, and the 99. Divide it by the total number of offspring and multiply by 100, and we get 3.25 map units. Okay, so now we take the information that we got from this round of it and also from the round between the wax and the shape genes, and we can build our map. So we lay out, you can draw a line and then put each of the traits in the gene order that we determined earlier, and then label with the map units the distance between them. So between the wax and the shape gene, we had 29.22 map units, and between the shape gene and the color gene, we had 3.25 map units. And these obviously are not giving the best visual of the distance there, but anyhow. Okay, so now let's figure out the interference. So to do this, we take our map units between the different genes and convert them back out of the percentage form. So like the 29.22 will switch back to 0.2922, and the same thing with the 3.25. So we multiply those numbers together, 0.2922 times 0.0325, and we get this number here, which is giving us the frequency of the double crossovers that can take place. We take that information, this number here, and we're going to multiply that frequency to the total number of offspring that we had in the F1 generation. This will give us the number 63.7, and it's kind of weird to have a decimal for offspring because you're not going to have 0.3 or 0.7 of an offspring, but just go with us on this one. This is basically saying this is going to tell you the number of offspring that you would expect to have the phenotype of what took place when there was a double recombination. So we use that information, and that's how we can determine our interference. So we take this expected offspring number, the 63.7, and then we figure out what the observed offspring were that were that way. So the two groups that were the smallest groups are the ones where the double recombination takes place. So we tally those two groups together, the 20 and the 15, and we get 35 observed offspring. And we divide that by what we would expect the number of offspring to be. That gives us 0.5495, and again, there's a lot of decimals throughout the process, so sometimes you might be like 1 or 2 off on there, and there's a little bit of a range. We take that number and plug it into this final equation here, and so it's 1 minus this number, and that gives us that the interference equals 0.45 or 45%. So we have 45% interference. So I hope that this video was somewhat helpful just to be able to walk through and understand this process. It can look a little bit messy and kind of confusing. The main thing is that it's more a matter of just keeping track of which genes and alleles you're swapping. So it's a lot less of a complicated equations and much more of just being able to go slowly and keep track, because it's just easy to make little tiny mistakes. But really understanding the concept, I think, is not too bad. And again, if you have questions, please email me and I can try to go through this in a different way that can help you if these didn't make sense. All right.